Some 15 minutes after class.
Okay. Okay. So somebody asked me a good question. They said, why do these have to, who said these are going to be small, right? Why are we going to get this vanishing gradient, right? Because who said they're going to be small, right? And I said, well, they can be small. And the reply was, yeah, but it's for the many to be small is unlikely, which is true, right? Sounds true, right? For many of them to be small, it's small chance of that if we're just relying on random. But the answer is that the activation functions are typically sigmoid and tan H. And those have gradients, which are almost all the times. Those will be, right? If you think of the slope of the tan H, most of the time, it's not very big. The sigmoid function, the gradient, is not very big. In fact, actually, he drew the picture of the gradient, right? And so, anyway, the argument is that most of the time they'll be small. You will get for a long chain of this, we'll get a lot of very small numbers. Okay. I think that's the argument. Then also, but what about the Rayleigh? What if we use Rayleigh? Then, then you only have two derivatives, either 1, 0. But that a lot of times that would be 0. Okay, fine. But anyway, for a lot of times that's going to be 0, and then you get it. That's obviously. I mean, actually, no. If you ever get 0, that's a problem, right? If any point in the chain you get 0, then you get 0, right? And actually, there's a lot of times when it's 0 because of some reason. Oftentimes, you'll get a negative input into the Rayleigh function. Can't think about it now. For some reason, you'll get a negative input into the Rayleigh function. Then you'll get a 0 for the derivative. Right? So then once you get anytime you get a 0, it's gone, right? Okay. So actually now I want to go back to some other questions. We'll come back next time to the deep neural networks, and we'll do convolutional neural network next week, and do what else. But now I want to go to my favorite place, which is YouTube. And I want to go to entropy. That's where I want to go first. Entropy.
Across America, BP supports more than 250,000 jobs to keep our energy flowing. Jobs developing lower carbon energy and keeping oil and gas flowing with fewer emissions. It's and, not or. That's how BP is investing in America.
If you want to be on camera, you want to be behind the camera, you want to do radio, podcast, whatever it is, this.
Yes, you can.
So we want to talk about this thing called entropy. Then we're going to talk about cross entropy. So let's take a look at this. Yeah.
Can understand entropy. Hooray! StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about entropy for data. Science, and it's going to be clearly explained. Note, this StatQuest assumes that you are already familiar with the main ideas of expected values.
So hopefully you're all familiar with expected value now, right? X, P of X, right? That tells us like the middle of the distribution of the random variables.
If not, check out the quest. Entropy is used for a lot of things in data science. For example, entropy can be used to build classification trees, which are used to classify things.
Here, we want, we have to decide what, okay, first of all, we have to decide what should be at the top of the tree, which node, which variable should be at the top of the tree. Like, should I put outlook up here? Or should I put humidity up here? Right? So basically the idea is we want to follow the path where we get the cleanest split. So I'd like it to be that, like, for example, when I go from here to here, it's a different question, but when I go from here to here, I'd like it to be that, everything when I go from here, when I go to here, given that I started here, everything is not playing golf. That's what I'd like. That would be best. Then I could just stop right here and say, I have a rule that gives me 100%. Otherwise, it's not 100%. Then I'll try and split it again or try and go down again. And so that brings up the idea of sort of what they call the purity of the node. It means, is it, what's the split? Is it all not play? That would be, pure. Or if it's 50-50, that's kind of impure. Okay? And entropy can be used to measure that, the purity of the node. So that can be used here.
Things. Entropy is also the basis of something called mutual information, which quantifies the relationship between two things. And entropy is the basis of relative entropy, aka the Kullback-Leibler distance, and cross entropy, which show up all over the place, including fancy dimension reduction algorithms like t-SNE and UMAP. What these three things have in common is that they all use entropy, or something derived from it, to quantify similarities and differences. So let's learn how entropy quantifies similarities and differences. However, in order to talk about entropy, first we have to understand surprise. So let's talk about chickens. Imagine we had two types of chickens, orange and blue, and instead of just letting them randomly roam all over the screen, our friend StatSquatch chased them around until they were organized into three separate areas, A, B, and C. Now, if StatSquatch just randomly picked up a chicken in area A, then, because there are 6
You just force them all into these receptive boxes. Okay, so now, if you randomly choose a chicken from here, of course, you're going to get an orange one. If you do it from here, of course, you're going to probably get a blue one. And here, though, we don't know what we're going to get, right? So we're going to see that the entropy here, the entropy is like a measure of the uncertainty. And he'll show that, but it's like a measure of the uncertainty. So we're really uncertain here, but we're not uncertain here or here. Okay, so it turns out that entropy will do that, measure that.
6 orange chickens and only 1 blue chicken, there is a higher probability that they will pick up an orange chicken. And since there is a higher probability of picking up an orange chicken, it would not be very surprising if they did. In contrast, if StatSquatch picked up the blue chicken from area,
It'd be surprising if you got an orange one, right? It would be surprising if you got a blue one. You got an orange one with the blue. He's trying to explain this concept of surprise right now. The contrast is if they picked up a blue chicken from area A, we would be surprised.
area A, we would be relatively surprised. Area B has a lot more blue chickens than orange. And because there is now a higher probability of picking up a blue chicken, we would not be very surprised if it happened. And because there is a relatively low probability of picking the orange chicken, that would be relatively surprising. Lastly, Area C has an equal number of orange and blue chickens. Thus, regardless of what colored chicken we pick up, we would be equally surprised. Combined, these areas tell us that surprise is, in some way, inversely related to probability.
Okay, so here, if there's a high probability of this, then we wouldn't be surprised about getting this, right? And if there's a low probability here, then we would be. So he says it's inverse relationship, inversely related to probability.
In other words, when the probability of picking up a blue chicken is low, the surprise is high. And when the probability of picking up a blue chicken is high, the surprise is low. Bam! Now we have a general intuition of how probability is related to surprise. Now let's talk about how to calculate surprise. Because we know there is a type of inverse relationship.
So actually, I think I gave you homework problem. I said it was worth 0 points, but I asked you to think about how to calculate. That has nothing to do with surprise, but how to calculate means like to come up with a number, or like we call that a measure, right? When you come up with a number. So, I asked you to come up with a number for talking about the difference between those two distributions, right? And here we want to come up with a number for surprise. How do we measure surprise, right? So I don't know how could we measure this? Well, I guess we could use just the inverse of probability, because we just saw that it's inversely related to probability. So if the probability was 1/9, we could say that surprise is 9. If the probability is only 1/4, then if the probability is larger and it's 1/4, then we could say the surprise is 4. So in the first case, it would be more than in the second case, right? Because the probability in the first case is less than in the second case. Right? Okay. So anyway, we want to measure it somehow. So maybe that way is not so great for some reason, right? Maybe that's not such a great way, but it sounds like a good start, right?
Between probability and surprise, it's tempting to just use the inverse of probability to calculate surprise. Because when we plot the inverse, we see that the closer the probability is to 0, the larger the y-axis value. However, there's at least one problem with just using the inverse of the probability to calculate surprise. To get a better sense of this problem, let's talk about the surprise associated with flipping a coin. Imagine we had a terrible coin, and every time we flipped it, we got heads. Blah, 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 blah. Ugh, flipping this coin is super boring. Hey StatSquatch, how surprised would you be if the next flip gave us heads? I would not be surprised at all. So, when the probability of getting heads is 1, then we want the surprise for getting heads to be 0. However, when we take the inverse of the probability,
Right. So if the probability is 1, which he's sort of suggesting that the probability of heads here is 1, that's complete certainty. Then we want the surprise to be low, right? Not low, it's 1.
of getting heads, we get 1 instead of what we want, 0. And this is one reason why we can't just use the inverse of the probability to calculate surprise. So, instead of just using the inverse of the probability to calculate surprise, we use the log of the inverse of the probability.
Now, log is like, why do they use log, right? Must have been some other way to fix that problem rather than throwing in log, right? But let's just remember what log is, how it works. And I think, if you can days, hopefully you remember that log xy. This is
Log X plus log Y.
log x plus the log. Maybe I hope you remember that. Anyway, we all learned that, right? And also you know that you can have different bases for the log, right? So you can say, what's the log base 2 of 8? Okay. And the answer is 3. And why is that? Because this question is really the same question. You can just write it a different way. You can say 2. I want to know what this is, right? So I can say this is the same. 2 to the what gives me 8. These are the same questions, right? And the answer is 3. So if I ask you what's the log base 10 of 1,000, then that's again a question, right? So that's the same question as n what gives me 1,000. That's obviously 3, right? Okay, so we can have different bases. We know that, right? And then, a lot of times we use the ln, the natural log, which really means log base e, right? And e, is a number, right? So that just means the base, which is this part would be e, right? And also because of this, we also know, I don't think we need to do this right now, but whatever base it is, well, put the base here, x, right? So I'm talking about the base b, that could be 2, it could be 10, it could be whatever it is, right? So if you do log of this, x, did I do that right? I think that's right. Log, I think yeah, I did it right. So, for example, this is, well, yeah, that's that, right? So the question, if we rewrite this, we're saying, what do I have to raise this to get this? Right? That's what I said, right? What do I have to raise this? Right here, I said, what do I have to raise this to get this? So this is, what do I have to raise this to get this? The answer is x. So that means that so we have a name for that, right? We have a name for when we have one function and we put in another function, we get x. What's the name for that? We've talked about it many times. They're inverses of each other, right? F and g are inverses, right? Like, for example, x squared and the square root of x, right? When you put in x squared into the square root of x, you get x, and we call those inverses. And same thing here. In general, g would be called the inverse of f. And so here, you can see that the log and the exponential version of it, using the same base, in other words, are inverses because they give you x. Okay, so, and that means that we know, we said before that we can see the pattern between a function and its inverse, right? It was the reflection through the 45-degree line, right? So that means that e to the x, which looks like this, it's an e to the x or b to the x. Well, it depends on b. B is a positive number. No, b is greater than 1. It looks like something like this. So the inverse is the log will be the reflection of this. Okay. So with this one, we consider growing extremely fast. So this one we can consider growing extremely slow. Okay, so anyway, but this is what we need right now. This is this is the way logs work. And so if we have this, then that is
Log X minus one.
log of x times 1 over, that's probably not. Anyway, I can't remember how to do this, but you can do it. This is equal to the log of x minus the log of y. Okay, that's easy to show that. Didn't I do that right?
Yeah.
So, and then one more thing. And the log of 0 is what? Well, no, sorry, the log of 1, sorry. Log of 1 is 0, right? You can see that here. Log of 1 is 0. Okay, so then so if I have the log of 1 over p, you can write that as what? The log of 1 minus the log of p, right? And the log of 1 is the log of p, right? The log of 1 we just said is 0. So we're going to get this, it's minus the log of p. Okay? That's just a review of logs because we needed that here.
Now, since the probability of getting heads is 1, and thus we will always get heads and it will never surprise us, the surprise for heads is 0.
So
In
that worked out,
contrast, since the probability for getting tails is 0, and thus we'll never get tails, it doesn't make sense to quantify the surprise of something that will never happen. So when we plug in 0 for the probability, and use the properties of logs to turn the division into subtraction, the second term is the log of 0. And because the log of 0 is undefined, the whole thing is undefined. And this result is okay because we're talking about the surprise associated with something that never happens. Like
Okay.
the inverse of the probability,
trying to model surprise. Trying to get a formula for surprise, right? So this is his suggested formula for surprise. Log of 1 over p. Weird, but that's what it's using, right? That's what.
the log of the inverse of the probability gives us a nice curve. And the closer the probability gets to 0, the more surprise we get. But now the curve says there is no surprise when the probability is 1. So surprise is the log of the inverse of the probability. Bam! Note, when calculating surprise for two outputs, in this case, the two outputs are heads and tails, then it is customary to use the log base 2 for the calculations. Now that we know what surprise is, let's imagine that our coin gets heads 90% of the time, and it gets tails
It's not all the time, like the last example, it's 90% of the time, right?
10% of the time. Now let's calculate the surprise.
Let's calculate the surprise for that, right? Okay, because that's a more standard thing. We don't want to generally calculate the surprise for something that's certain, which is what he did before. That's not very interesting, but here, this is more interesting. So this is when you have 90-10, right? Okay, so what is the surprise? Well, it's just this, right? So that's this. That's minus the log of 0.9, right?
For getting heads and tails. As
There we go. And so the surprise for this is not very surprising. The surprise for this is more surprising.
expected, because getting tails is much rarer than getting heads, the surprise for tails is much larger. Now let's flip this coin 3 times, and we get heads, heads, and tails. The probability of getting 2 heads and 1 tail is 0.9 times 0.9 for the heads times 0.1 for the tails. And if we want to know exactly how surprising it is to get 2 heads and 1 tail, Then we can plug this probability into the equation for surprise and use the property.
Why do we multiply these? Because they're independent, right? So we know that we have multiplication for independent. We have, what's the surprise? I'm sorry, what's the probability for this? It's this. So what's the surprise for that? It's 1 over that log.
Properties of logs to convert the division into subtraction, and use the properties of logs to convert the multiplication into addition. And then plug and chug. And we get 3.6.
So anyway, interesting is that when we do the surprise, well, we see the answer, right? Which is that. But we saw that also, we started out with the log of product, but it became the sum of the logs. And now each one of these in the sum is the surprise for each toss, right? This is 90% chance because it's heads, 90% chance because it's heads, and 10% for tails. And so the surprise is the sum of the individual surprises, right? That's what's happening here, right? This is the surprise, but by log properties, this becomes this, but these each happen to be a surprise for each of the coins. So we can say that it's the sum of the surprises. So that's kind of a nice property. So the surprise for a kind of compound event So the surprise, that's just that's a nice thing that just happened, right? Didn't have to happen, but it did, right? So the surprise for this whole thing, which is here, turns out to be the sum of the surprises of each piece, right? So that's nice, right? Okay, so anyway, we calculate the sum of the surprises. We get this. Okay.
6.2. But more importantly, we see that the total surprise for a sequence of coin tosses is just the sum of the surprises for each individual toss. In other words, the surprise for getting 1 heads is 0.15. And since we got 2 heads, we add 0.15 2 times, plus 3.32 for the 1 tail, to get the total surprise for getting 2 heads and 1 tail. Medium bam. Now, because this diagram takes up a lot of space, let's summarize the information in a table. The first row in the table tells us.
Okay, so we just put the table here, and he puts the probability here, and the surprise here, right? So that's okay, right? So we can see that when the probability is this, we calculate the surprise, and we got this. Oh, it was this, we got this.
The probability of getting heads or tails. And the second row tells us the associated surprise. Now, if we wanted to estimate the total surprise after flipping the coin 100 times, we approximate how many times we will get heads by multiplying the probability we will get heads, 0.9, by 1.
He's just assuming that if you toss it 100 times, that you're going to get 90% heads, which is a reasonable assumption, right? So if that happened, then this is the number of times that we're going to get heads, right?
100. And we estimate the total surprise from getting heads by multiplying by 0.15.
Each time that happened, we would get this much surprise, right? So we'd have to add up this 90 times, right? Does everyone get that? And then we could do the same thing here with 10 of this surprise. right? So we would have to add up this 10 times, right? And this is going to give us the expected surprise. In other words, it doesn't really happen this way, but this is what we would expect to happen. We're not saying it's really going to get exactly 90 tails and 90 heads and 10 tails, but that's exactly what expected value is. That you say what you would expect to get. You calculate that based on that, right? So we can get the expected surprise, right? For 100, we can get the expected surprise, right? Actually,
So this term represents
we have to divide by 100 to get the expected surprise.
how much surprise we expect from getting heads in 100 coin flips. Likewise, we can approximate how many times we will get tails by multiplying the probability we will get tails, 0.1, by 100. And we estimate the total surprise from getting tails by multiplying by 3.32. So the second term represents how much surprise we expect from getting tails in 100 coin flips. Now we can add the two terms together to find out the total surprise, and we get 46.7. Hey, StatSquatch is back. Okay, I see that we just estimated the surprise for 100 coin flips. But aren't we supposed to be talking about entropy? Funny you should ask. If we divide everything by the number of coin tosses, 100, then we get the average amount of surprise per coin toss, 0.47.
Okay, so that's the average amount of surprise, right? Per coin toss, for the expected surprise. So what is the expected surprise?
So, on average, we expect the surprise to be 0.47 every time we flip the coin. And that is the entropy of the coin.
What is the entropy? The entropy is the expected surprise. Okay, and what is the surprise? What?
Inverse of probability.
Right, the log. Or actually, I think it's minus the log, right? Minus the log of the inverse of probability, right? Because there is a minus, right? That is the entropy. So it's the average or the expected surprise. The entropy, I said earlier that the entropy was what? I said it was a measure of the uncertainty, right? And now we're saying that it's the average surprise, which is, I guess, that.
Expected surprise every time we flip the coin. Double bam! In fancy statistics notation, we say that entropy is the expected value of the surprise. Anyway, since we are multiplying each probability by the number of coin tosses, 100, and also dividing by the number of coin tosses, 100, then all of the values that represent the number of coin tosses, 100, cancel out. And we are left with the probability that a surprise for heads will occur times its surprise, plus the probability that a surprise for tails will occur times its surprise. Thus, the entropy, 0.47, represents the surprise we would expect per coin toss if we flipped this coin a bunch of times. And yes, expecting surprise sounds silly, but it's not the silliest thing I've heard. Note, we can rewrite entropy just like an expected value using fancy sigma notation. The x represents a specific value for surprise, times the probability of observing that specific value for surprise. So, for the first term, getting heads, the specific value for surprise is 0.15, and the probability of observing that
Surprise is the random variable, and its values, we multiply its values times their associated probabilities, right? So that we can get, for this random variable, the outputs are the surprise. Surprise is the random variable. We multiply that times the probability of that surprise, right? And that's the expected value. Okay? Surprise here is a random variable. That's the expected surprise. And how do we get that? We multiply each possible value of surprise times its probability. And here, the possible values of surprise are when it's a head, it's 0.15, and when it's a tail, it's 0.32. I'm sorry, 3.32. Right? So that's the random variable. Like we talked about random variables, looked at it, and you can talk about the random variable having different values of the dice, 1, 2, 3, 4, 5, 6, or what other examples? Number of defective items in you select a couple transistors. You select 2 transistors from a manufacturing process, and so how many defective can you have? That could be a random variable. You might have 0 transistors in your little sample that are defective, or you might have 1 transistor, or you might have 2. So you have 3 possibilities for that random variable. Or you could toss a coin 3 times. Then you could ask that, and you could let the random variable be the number of heads. So you could have, what are the possibilities for the number of heads? 0 heads, 1 head, 2 heads, or 3 heads. Right? So that's the random variable. But here, the random variable is the entropy. So do an experiment like tossing this weird coin, right? This is a weird coin, right? And the random variable we're talking about is not the number of heads, not the number of tails. Random variable is the surprise. And if you get a head, you get a certain surprise. And if you get a tail, you get a different surprise, right? Because especially it's different because it's not a fair coin, right? So you get 2 different surprises, and then you multiply those outcomes, each of them, by the random variable, by the probability, and that is the expected value for the surprise. That is what we call the entropy. Okay?
That surprise is 0.9. So we multiply those values together. Then the sigma tells us to add that term to the term for tails. Either way we do the math, we get 0.47. Now, personally, once I saw that entropy was just the average surprise that we could expect, entropy went from something that I had to memorize to something I could derive. Because now we can plug the equation for surprise in for x, the specific value. And we can plug in the probability. And we end up with the equation for entropy. Bam!
Right? Everybody get it?
Unfortunately,
I was going to say, unfortunately, the guy that invented this idea was, his name was Shannon, and he did that, I think in his master's thesis at MIT. And anyway, he just reversed the order of this. That's all. But other than that, it's the same. I think, wait, let me make sure that.
even though this equation is made from 2 relatively easy to interpret terms, the surprise times the probability of the surprise, this isn't the standard form of the equation for entropy that you'll see out in the wild. First, we have to swap the order of the 2 terms. Then we use the properties of logs to convert the fraction into subtraction. And the log of 1 is 0.
Right? This is this. Then log of 1 is 0. We get this.
Then we multiply both terms in the difference by the probability.
Right, so it doesn't have 1 over p at the end. So the standard form is this. But now you don't see surprise in there, right? So he doesn't like that, right? He prefers the other one, this one. So now, in this way, we can see that it's just the expected surprise. Now you can't really see that anymore, right? But it is the expected surprise. That's one way to think of it, right? Okay, but this is the standard way to see it. All right? So what is it? It's sigma p of x, just log p of x. Okay, not 1 over p of x here, but you do get the minus out here. Okay?
Then, lastly, we pull the minus sign out of the summation. And we end up with the equation for entropy that Claude Shannon first published in 1948. Small bam. That said, even though this is the original version and the one you'll usually see, I prefer this version since it is easily derived from surprise, and it is easier to see what is going on. Now, going back to the original example, we can calculate the entropy of the chickens. So let's calculate the entropy for area A.
Okay, now I said that entropy is a measure of the disorder. Did I say disorder? I said uncertainty. So measure of the uncertainty. So where do we have more uncertainty in terms of what's going to happen? Here, or B, A or C? C, right? C is more uncertain than A, right? We're pretty certain about what's going to happen here, right? So hopefully the entropy will be higher here than here.
Because 6 of the 7 chickens are orange, we plug in 6 divided by 7 for the probability. Then we add a term for the 1 blue chicken by plugging in 1 divided by 7 for the probability. Now we just do the math and get 0.59. Note, even though the surprise associated with picking up an orange chicken is much smaller than picking up a blue chicken, there is a much higher probability that we will pick up an orange chicken than pick up a blue chicken. Thus, the total entropy, 0.59, is much closer to the surprise associated with orange chickens than blue chickens. Likewise, we can calculate the entropy for area B. Only this time, the probability of randomly picking up an orange chicken is
Here, it should be even smaller. Right? The expected surprise is even smaller.
1 divided by 11. And the probability of picking up a blue chicken is 10 divided by 11. And the entropy is 0.44. In this case, the surprise for picking up an orange chicken is relatively high, but the probability of it happening is so low that the total entropy is much closer to the surprise associated with picking up a blue chicken. We also see that the entropy value, the expected surprise, is less for area B than area A. This makes sense because area B has a higher probability of picking a chicken with a lower surprise. Lastly, the entropy for area C is 1. And that makes the entropy for area C the highest we have calculated so far. In this case, even though the surprise for orange and blue chickens is relatively moderate, 1, we always get the same, relatively moderate, surprise every time we pick up a chicken. And it is never outweighed by a smaller value for surprise like we saw earlier for areas A and B. As a result, we can use entropy to quantify the similarity or difference in the number of orange and blue chickens in each area.
That would be for the decision tree. We said we want to measure how pure it is, right? That's similarity or difference. We can use this, measure how pure a node is in the tree, right?
Entropy is highest when we have the same number of both types of chickens. And as we increase the difference in the number of orange and blue chickens, we lower the entropy. Triple bam! P.S. The next time you want to surprise someone, just whisper, the log of the inverse of the probability. Bam. Now it's time for some.
So that's entropy. Now let's start, we have a little more time. Is it in a hurry? Let's just do a little bit more. Because let's look at cross entropy. We won't get to watch all of it. It's just cross entropy is not entropy. Okay, so don't think that it's entropy.
How to get the most of Grammarly free.
It's Kayla on behalf of Grammarly to tell you all.
If you made a neural network on the surface of Mars, you'd be a long, long way away from me. That's the truth. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about Neural Networks Part 6, Cross Entropy. Note, this StatQuest assumes that you already understand the main ideas behind neural networks, the main ideas behind backpropagation, and softmax and argmax. If not, check out the quests. The links are in the description below. Now, before we get started with cross entropy, let me remind you that in the StatQuest on backpropagation main ideas, we had a simple neural network with a single output that, in theory, could give us any output value. In cases like this, we commonly use the sum of the squared residuals to determine how well the neural network fits the data.
Okay, so, right, this is familiar, right? The observed means what? Or what is the predicted? That's what we predict. And the observed is what's actually there, right? So there's an error, a difference between them, right? Right? Everyone recognizes terminology. So the observed, there are other words that people use for the observed, like they use the ground truth. They call it the ground truth. Okay, so it's just the thing that you actually get as opposed to predicted. And they also use the gold standard. I don't know if that's used so much anymore, but it's like, it's really there. Okay, and there are other words also. Okay, so you can use lots of different words, but the idea is that we have the predicted versus the actual. Right? So he's talking.
Bam. Now, when we have a neural network with multiple output values, we often run the data through argmax to make the output.
The argmax just gives you, we said that softmax gives you a probability in here, but the argmax just gives you 1 or 0. Okay, so it gives you, like, you can just pick it out, right? If it's 1, that's the answer. That's what we're predicting. Okay, but this argmax doesn't work for backpropagation, so that's why we use softmax. Okay.
Easy to interpret. But because argmax has a terrible derivative, we can't use it for backpropagation. So, in order to train the neural network, we use the softmax function. And the softmax output values are predicted probabilities between 0 and 1. And when the output is restricted to values between 0 and 1, we often use something called cross entropy to determine how well the neural network fits the data. Cross entropy is one of those things that sounds super fancy and complicated, but when it comes to neural networks, is super simple. To see how super simple it is, let's start with this super simple training dataset that has petal and sepal widths for known or observed iris species. Now let's plug in the petal and sepal widths for the first observed species, Setosa, and run the numbers through the neural network, and run the raw output values through the softmax function. Beep, beep, boop, beep, boop, boop, beep. Now, because we know the data are from Setosa, the cross entropy is the negative.
Said he's putting through a Setosa flower, right? So, and now here, this is what he got out, and it was so the prediction will be correct, right? Didn't have to be, but it is.
Negative log base E of the softmax output value for Setosa, 0.57. In other words, we plug the predicted probability for the observed species into the cross-entropy function. Note, if you have seen the cross-entropy function before, this version may look different to you. The difference is because neural networks only need a simplified form of this general equation. In this summation, M is the number of output classes. In this case, M equals 3 because we have 3 output classes, Setosa, Versicolor, and Virginica. Thus, if we expanded the summation, we would get 1 term for Setosa, 1 term for Versicolor, and 1 term for Virginica. Now, because we know that the data from the first row
This later. So we'll go through this to get the idea of the cross entropy. Then we'll talk about something called the KL divergence. And you already worked on the KL divergence because I asked you to come up with that measure. By the way, what did anybody come up with anything?
Rate of change.
What did you get?
We got like the rate of change.
Sorry.
Calculate the rate of change from year 1 and year 2.
And how do you do that? What did you mean by that?
Initial value minus the change in year 1 and year 2 divided by initial into 100. It's like a percentage.
Yeah, like a percentage. Okay. Anybody else come up with anything? Hopefully you all tried to do it. So remember the question was you were teaching kindergarten students, and 1 year you said, okay, which do you prefer, apples, bananas, or cherries, right? And so some students say apple, some students say banana, some people cherry, and you just draw the graph of the percentages. Most people like apples, and some people like bananas, and some people like cherries, right? And you do this every year, and in the second year that you do it, you notice that it's, it was different. So the distribution was different, like a different percentage of apples, different percentage like bananas, and different like cherries. So my question is, can you come up with a measure of the difference? So like, one is like apple. Apple is 20%, bananas is 60%, and cherries is 20%, right? And then next year, it doesn't look like that. So next year, it's like 50% for apples and 40% for bananas and 10% for cherries, right? Yeah. So how can we say, obviously they're not the same, but I'd like to come up with a measure of how they're different. And by a measure, usually I'd like to have just a single number. So what can we do, right? Want to measure for how these two distributions are different, right? So what idea? So what did you say to do?
Rate of change.
So tell me the calculation.
So it's initial value 20. So
20.
it was 20 for A minus
Minus
50
50.
divided by, it was initially 20
Okay.
into 100.
Right.
Into 100.
Times 100.
Yeah. Just like calculating the percentage of
Oh,
change.
okay. That's just this part, right?
Yeah.
That's all you did?
So I did A, B, and C. I have percentage for A, B, and C.
Okay, so you did this for A, and then this
And then
for B,
and
and this for C. And then what?
we found rate of change for A was 300. Like for A was 0% because it did change.
Okay,
B it was minus 75%.
okay,
C was 300.
okay, and then you just left it like that.
Yeah.
Yeah, okay.
You can
That's good, but you could add them.
So like define the average, but
Okay, if you find the average,
But-
you could add them. A lot of things you could do, right? What are you gonna say, but what?
minus 75% is there. So I don't know if we can like take negative.
I don't know either, it's up to you. I just asked you to come up with something,
Yeah.
that's all.
That's all right.
Right? You're coming up with it, right? But you understand the problem, right? It's just to say how, to measure how these are different, Right, and you came up with a method, right? I would say at the end, you probably want to add them, or do something to collapse them into a single number, maybe the average or something like that. Then you'll say that, okay, now, and then you could say, okay, well, we could do it between this one and this one. How about between this one and, some other one? It's like this. How about compare this one with that one or something else, right? We'll come up with another number. And then, so we could use his method to compare distributions, right? And that's what we wanted. That was what the assignment was, to come up. Did anybody come up with anything else?
Assumption,
What?
like assuming, like if you assume X equal to this set of students, say 100 or 120, whatever it is. And from that, since every year it keeps changing, right?
But anyway, okay, I don't want to keep everybody too long. But anyway, there's other ways, right? We could do something else. Like how about, oh, you did do that. You subtracted this one minus this one minus, yeah, you could do that. Or though, maybe you could take a fraction. This one as a ratio of this one. This one is a ratio of this one. Then you could add those or whatever you wanted to do, right? You could multiply them. Who knows what you could do, right? And that would give you some number which you could associate with the difference between these two. So the thing is that that's what we want, is some way to measure the difference between two distributions. Okay, now we're going to go and cover something called the KL divergence. KL divergence. And that's a way to do it. I don't know if it's exactly what he did or what I just said. I forget what it is right now. But something like that. Okay? Then what we want to do is, so that's the way. Now, let's let these be the predictions for the class. Remember, we're predicting whether something's an iris setosa, an iris virginica, or an iris something else, right? Versicolor, right? And so let's let these be the predictions, right? We said you could get 20% and 8, right? We're using softmax. So the predictions are going to be percentages, right? So let's let these be the predictions. And let this be the actual. So the actual is going to be 100% one place and 0 everywhere else, right? And then we want to measure the difference between those, and that is basically going to, well, then we want to, okay, so then we're going to have a measure of the difference between the two, right? That's our error. We can use that as our error in softmax, right? Right, we can use that for the error because this is our prediction versus the actual, but the actual is a little bit strange. The actual is 100% 0, 0, right? And then we can measure this versus that. And that will be our measure for that we want to minimize, right? That's what we'd like it to be as small as possible, right? So we can use training to adjust towards that, right? And, okay. And that is basically cross entropy, but it's not exactly cross entropy. We'll see that it's almost cross entropy. In other words, minimizing the KL divergence, which is what I just said, wanted to minimize it, is basically minimizing, it is equal to minimizing cross entropy. So we don't minimize KL. They don't usually say we're minimizing KL divergence, minimizing cross entropy, because they're the same thing, but that doesn't, minimizing them is the same thing, but they are not the same. There's one more term. So it turns out that this thing, if we do KL divergence, is basically the cross entropy. But it's not. It's the cross entropy. I think it's plus the entropy. We just said it, the entropy just now. But the entropy actually doesn't have, at least in this case, doesn't have this in it. It only contains, doesn't have this in it. It only contains, it only has the actual. And the actual doesn't change no matter what we do. So if you want to minimize KL, you have to minimize this, but this you don't have to use because it doesn't change. So you just have to minimize this. So minimizing KL means, anyway, I'll repeat this next week after we make clear what the cross entropy is. But anyway, this is the key here. Once we really want to, as we said, we want to minimize this, right? Makes sense, right? Maybe they didn't define it exactly the way he did. Maybe they did. I forget actually. But we're going to use it to measure the difference between the actual distribution, which is 1, 0, 0, or 0, 1, 0, something like that, versus our prediction, which is something like this. And we want to train to get it as close as possible. So we're saying we're minimizing this. So we're minimizing this. This part just basically disappeared. It doesn't mean you don't need to minimize this because it doesn't have anything that changes it. So it doesn't matter. You don't need it there. Minimize sum. This is constant. You have to minimize this, right? So that's the idea. Okay, so we'll come back and talk about this again. That's the idea of cross entropy. Why you need to minimize cross entropy. It's actually you want to minimize KL divergence, but like I just said, you only have to minimize the cross entropy. Okay, that's all for today.
I didn't get one number. Year 2 of it. Year 1. And good. So I give you
Question? We'll finish that up again next time. And we'll also come back and talk about convolutional neural networks next time. What the KL is.
you can listen. T minus 0 or A will be 0. 40 n minus 40 minus 30 minus 30 over banana. That's the change for banana. Then A for 200 here. This kind of makes it defeats the purpose of this percentage because we don't know exact number of students to then assuming that 100 students are तो फिर ये करेंगे
तो तेरा लॉग इट 15 है 15
so I am not change तो 0 change B में minus 30%
एक हॉबी हो रही minus 30 को कैसे
change in banana change in students liking the banana from year 1 decrease by
increase
year 2 में
This
40 minus 10 that is 30%. So increase by 30%.
but
तो एक नंबर हो तो भी
Right.
because number of students नहीं दिया तो how can we do? If we assume that 100 students, तो फिर it becomes 100 करके 30. But that
Oh, right. Yeah.
they कुछ किया ना
I like it. Let's think about any of that relates.
entropy.
KL.
ये ना क्या दिक्कत? I was much.
Yeah, I think I'm gonna get these two ways to calculate them as well, get this.
even not able to get
Please. And, but actually, you know, there are a lot of other.
you would it.
distance
I
measures
give it to you.
besides-
If you have to join group, if you open,
Yeah, that's.
she's like, she will not
Let's think
allow
about how
interrupt.
that relates to
So,
balance. But.
3 days she has, today I will finish. I don't want to wait the,
The question is, what's the?
What is it?
Measure. This is what.
she is giving everything today.
Because it achieved,
She'll explain everything.
like I just said, so for
How to
KL.
get more. She'll give
They
more.
use KL.
Then what?
It's a user cross entry indicator. This. Right, minimizing this. And you could test with, so you could write your own function. Instead of softmax. So instead of cross entry, you could write this code and use it in the. Fill it in, so.
No. The only student at that time.
Just talk about it. It's a sequential one, right? Put in
How do I
the
see?
layer expansion. Relation, just at the end.
Yeah.
You could write your own, the activation is like, well, it's something that's like an argument for that.
Only one year.
Then you need to layer. Parameters.
Was that the digital transfer? Like AB 0.5.
Yes.
0.4.
Yeah.
Yeah.
Scale it up.
Not the
5.1.
activation.
Yeah.
Somewhere we specify cross entry. Somewhere along the line. Sequential. You say it's my process. So instead of using cross entry, you could write your own and then train the neural network. See how well it works. What are you doing? If this would try to use this, I mean, it might not be that hard. but
I feel this.
You know, if you write this, it's not so hard. And then getting it, when you're getting it to work, you know, writing it so that it functions well. It's sequential.
It's the requirement.
I don't know if that's true or not.
Because using other, I don't know. Ask it, like,
I think it's interesting. I don't know if anybody's tested this out before. She said, yeah.
if this approach is on site, everybody can take it. Yeah, this, the second one is, this makes more sense. Transfer to vectors, the vectors, you calculate this. Not like any more change.